I am Professor Torben Pedersen. I'm Professor of Computer Science at Aalborg University and co-founder and Chief Scientific Officer of FlexShape. And I'm going to talk about general, powerful, and scalable management of energy flexibility with FlexOffers. So as most of the people in this conference know, we are moving towards a bottom-up energy system. In the old days, power was generated centrally in power plants, went down through the transmission network and further down through the distribution network, where it was consumed. Today, energy is produced more and more bottom-up. So we have local solar, local wind, and so on. So the energy is increasingly produced bottom-up. Energy communities and microgrids is an example of that, but also many other cases. So we believe that we should also try to control the energy system bottom-up, since that's more natural and thus more effective. So what we want to do here is that we want to integrate energy devices and processes like PV panels, batteries, heat, and so on, business models, data, and computing to support users and their practices. And of course, we all know that the key to this is flexibility. We also need to integrate with the existing energy community and energy system, So the way we view things is that we see the emerging energy system as a cellular one, consisting of cells that are nested within each other and become bigger and bigger. So at the bottom, we have individual cells, which could be a prosumer with their own PV and battery and trying to do a mini energy community in their own house. Then they can be part of a larger district energy community where you try to reach self-sufficiency, save on CO2, and so on. But again, energy communities are embedded in larger energy communities, for example, the DSO grid and the TSO grid that they have to collaborate with. And each player in this system has their own roles, they have their own assets and capabilities. So this is sort of the grid view we have on the left. Then if we have the flexibility view, then actually each of these cells has to manage flexibility. So inside we have various devices, we have production, we have consumption, and this needs to be managed by a flexibility manager. But then no cell is an island, so you need to collaborate with your neighboring cells, which could be individual or energy communities, and you also need to interact with the market. And we believe that to do all this, we need a joint flexibility model, because there's flexibility in so many things. And if we do things the traditional way, what that we often see in this domain is that, well, okay, we have one kind of device. Say we have a battery, and we want to optimize that battery for the spot market. Okay, then we build one system there. Then, okay, if we want to optimize it for the intraday market or the reserve market, we build another system with modeling the battery, doing the optimization, doing the trading, and so on. So we get a lot of connections here, and each connection is a complex system. If we then have another load, like a heat pump, we do the same thing again and again and again, and we have many devices, we have supply, we have demand, and we have mixed devices. If we have to do this in the general case, say we have 10 markets and 100 different types of units, we need to build 1,000 complex systems. Instead, what we want to do is that we want to generalize the hard part of it, namely the optimization and management of flexibility and generation of bids towards markets. So the idea is, instead, in our approach, we want to model all these devices with FlexOffers, build connectors to them, so we have a flexibility representation here, and then we can build connectors out to the markets. Now you see we go from a product to a sum, so instead of 1,000 complex systems, we only have to build 110 simple connectors. So what is a good flexibility model? Well, first of all, we think it should be explicit. Traditionally, flexibility has been modeled implicitly. So if you have a price, you see what the response is and so on, but you don't know what the true flexibility is. We believe that explicit models allow capturing more of the true underlying flexibility. Also, a good model should be general. It should capture all, or at least most loads, also complex loads with state dependencies like heat pumps and so on. It should handle energy production, storage, energy conversion, and so on. It should also be aggregatable and disaggregatable. So we should be able to take many smaller loads, like in the kilowatt hour size, aggregate them to megawatt hour size, do trading in markets and so on, and then disaggregate back to find out when to turn on and off the individual devices. Also, because of this, it should be scalable. We should be able to aggregate thousands or even millions of loads very, very fast. And what we will see later is that if we have exact accurate models, we actually, by mathematics, cannot scale. So instead, what we think we need is good approximate models. So FlexOffers is a joint model for all types of flexibilities. And devices have different flexibility patterns. Of course, the simplest ones have no flexibility. So a wind turbine produces energy when it produces, and when we want to watch TV, we watch TV. There's no flexibility in that. So then we just have a simple power profile here. Here we have hours, and we have the power or energy in these 1 hour slices. The 1 hour is just for ease of presentation. Usually we work at a finer 5 or 15 minute granularity. Then some devices in a household, this could be wet devices like washers and dishwashers, they have a fixed energy profile, but they have time flexibility, so you can shift them from an earlier start time to a latest end time. And the user is happy as long as it happens within their specified bounds. Then we have even more complex loads where there's the time shift flexibility, but there's also the possibility to turn up or down the energy and power in each time slice. This could be loads with batteries, or like EVs, batteries, elevators, and so on. Also, industrial processes typically fall here. And then finally, we have, and in order to not just to go max or min in all the slices, we can also put in a total energy constraint saying, okay, what is the minimum energy we need, for example, EV to charge, and what is the max? So we can put a bound on how can this flexibility in amount be used over all the slices. Finally, if we have even more complex loads with intra-unit dependencies, for example, a heat pump or other kinds of heating systems, then basically flexibility depends on what was done in the previous slices. So if we, for example, if we have a heat pump, if we heat up a lot in the beginning, in the early slices, then we cannot keep on heating, in the later slices, because then the house becomes too hot, and vice versa. If we turn it off, we have to turn it on eventually. So the flexibility in the later slices depend on what was done in the earlier slices. We also support this. So let's have a simple example. So a consumer arrives home at 10 p.m., wants to recharge their EV battery at the lowest possible price, or CO2, by 8 a.m. in the morning. Then we have 10 p.m. is the earliest start time, 8 a.m. is the latest end time, which makes 6 a.m. the latest start time. The consumer's local energy management system, flexibility system, generates a flex offer, which is offered to an aggregator or a market, and the negotiation with the aggregator is started, and this is accepted. And then the buyer of the flex offer then decides, okay, when do we put this? So when do we start charging so that there's a lot of cheap and green energy available and the grid load is low? So for example, at night. Later, we reward the consumer for the flexibility, perhaps month by month. The flex offer has an well-defined model with a number of definitions and constraints that we see here. And it also has a well-defined protocol for which phases you must go through. First, you offer it, the utility or aggregator that you negotiate with will receive it, they can accept it, and so on. And if they accept it, then they have the right to schedule it. That doesn't have to happen immediately. They may also reschedule it and so on before it's finally executed, and later there's a billing phase. interesting properties is that we have an exact location, so we know the exact meter and can then aggregate up to radial and transformer and so on. It's aggregatable. We can put in total energy constraints, slice dependencies, and so on. We can handle production and mixed loads, grid capacity constraints, and so on. And it's an offer. So there you have a flex prosumer with some flexibility that offers their flexibility to whoever wants it. So there's no force or curtailment here. But when you offer and someone takes you up on the offer, you also have commitment. We think this is the right way to do it. So if we look at the hierarchical view, we sort of start with device level consumption data. Then by using that, we predict demand. We then model flexibility, so create individual flex offers for each of these devices down here. Then we take all the small Lego bricks and aggregate them into bigger Lego bricks. So the green ones here become this ones, the orange ones becomes this one. And then we have megawatt hour flex offers that can be balanced and scheduled by trading on the market and solving problems at grid level. Once we have sort of placed the big flex offers, we can disaggregate and go down with schedules and see how we execute them. Good. So if we look more at a process view, we have data from IoT devices. We collect the data, we do pre-processing, remove outliers, fill missing data, do some aggregation and so on. We do some predictive modeling with machine learning, do demand prediction, take in context like weather and so on, and use that to generate flex offers that we then aggregate, trade, schedule, and execute. So we use specialized constraints to characterize different types of flexibility, like the start time constraint, the energy amount constraint in each slice, the total energy constraint, also the dependent energy constraint. So how much energy do I need to use in this slice, depending on what I did in earlier slices. For example, for heat pumps, we have an acceptance time constraint. So this is from my offer until you have to say yes or no, how many hours and so on can I leave. And then later we have an assignment time constraint with this, how much prior to the actual execution do I need to know? So we can set all these things depending on our wishes and device types. So the general flex offer generation process is like this. So we have time series and context information, we do data pre-processing, and then we basically try and extract the time flexibility and the amount flexibility separately because they require different techniques. Then we put them together again, and we have a flex offer, and then we can evaluate that in terms of models, in terms of economy, and so on. So the input data is energy consumption profiles for a number of days and weather and context. Then we sort of specialize this process for different types of devices. For example, for a wet device in a house, we need to forecast when is it actually switched on, when would the user typically want to switch it on, and then we can of course suggest to move it around. And once they switch it on, how long does it run for? And then we can also estimate when is it turned on the next time, and what is the energy profile. And then the idea is that the time between activations, we can actually have some flexibility there, because the next activation is when the user would need to have their clothes or dishes, but we can then have some flexibility. For EVs, we need to also do some domain-specific things. So we need to estimate when it's plugged in, what is the battery level, and when is it plugged in. So we need to forecast when is it plugged in, when is it plugged out, and so on. And we need to estimate the battery level, how fast can we charge, how long do we have to charge, and the energy profile, and then we put that together in a flex offer. For heat pumps, we again have to estimate some things, and basically a heat pump is more or less, you can think it's running all the time, so there's no time flexibility, but you can turn up or down the power in each time unit. So we need to estimate parameters and generate models. Then we need to do temperature forecasts depending, okay, so how much power and how much do we charge, how cold is it outside, what is the sun, and so on. Then we can make a flexibility model and calculate the min and max energy that we need for the 24 hours to stay within our comfort range, which could be 20 to 24 Celsius. And then we generate a flex offer. And we do parameter estimation using simple linear time invariant models like these. Then when we aggregate, we start with small flex offers from consumers, we aggregate them into larger ones, and we might even aggregate again. So this can be a multi-step process taking, aggregating within the prosumer, within the energy community, even at the district level and so on, at a BRP level, and then getting to a large offer that you can trade on markets and schedule and disaggregate again. So how do we do this? So when we aggregate, we have a number of requirements. So first of all, aggregation, we will actually tend to lose flexibility. So we want to preserve flexibility when we aggregate, because if you have two units that can move independently, if you put them together, you sort of put them in lockstep, and thus you lose some time flexibility. But we want to preserve as much as possible that. We want to aggregate as much as possible. So going from having very many to having few large ones. And then when we aggregate, we also want to be able to disaggregate. We want this to be very fast, depending on the configuration. We have only a few minutes or even few seconds to do this. And we want it to be very scalable and handle millions of flex offers. And the process is like this. So first we have the individual flex offers here with their profile and their flexibility in amount and time. And then we found out it's smart to take ones with similar parameters, like similar start times and so on, and group them together. So here the two top ones and the three bottom ones, they actually go together. And then optionally, we can also try and bin pack, depending on what we want. If we want to have a flat profile to do peak reduction, or we want to follow a load curve and so on, we want either short and tall or long and flat and so on, we can do some bin packing. And then finally, we take the slices of each and put them together to sort of do so-called N-to-1 aggregation and end up here with one flex offer for each of these groups. Also, we can capture price information. So for example, we can capture a deviation price with what is the price of a 1 kilowatt hour deviation from the baseline. This can also be encoded into the flex offer. And basically, we can see flexibility as an asset that we can put a price on. So for example, we can say, okay, I can sell this flex offer every day for the next month, and then the DSO could buy it and use it to avoid just grid congestion. And then we can have dynamic prices based on when is it offered, where in the grid is it, what kind of flexibility is it. For example, if you have flexibility in a location in the grid that's very congested, then it's of course worth more than if you're sitting close on a transmission line with no capacity constraints. And then we integrate it with markets in this way. So basically we have these agents that make the interfaces to the production, to the consumption, to the hybrid loads. We have a manager that can then aggregate and generate bids and so on, and then send out the bids to the different markets. So key experimental results include these. So flex offers can be effectively generated from data. So it's not like we have to have a lot of manual work to generate this flexibility. Flex offer aggregation can scale. It can scale in the amounts of flex offers and in long timestamps. For example, a whole day of 15-hour time intervals gives you 96 timestamps. Exact models like the LTIs we just saw, they don't scale at all. They have an exponential complexity and they cannot handle long time scales. And basically the most advanced type we have is the one called the dependency-based flex offer, which allows optimization of thousands of loads, captures a lot of flexibility, unlike the base flex offers that we had first, because they can do these inter-slice dependencies, can be efficiently aggregated and disaggregated, and can also be visualized. If we look at typical exact models like LTIs and polyhedrons, they cannot scale they capture a lot of flexibility because they're exact, but that's sort of it. They cannot scale, they cannot be aggregated and disaggregated, nor visualized. And actually what we found out is that this process of first aggregating, then scheduling, and then disaggregating, it's faster than trying to schedule all the small loads individually, which is what you often see, but actually it also gives better utility, for example, in terms of balance prices, CO2, and so on. So it's actually a better process as well. And we have shown that aggregated flex from FlexOffers can be traded in several markets, and we can do optimizations for price, CO2, grid capacity, etc. So we have used this technology in more than 15 projects, starting back in 7th framework program and going on to Horizon 2020 and so on. You see a partial list here at the bottom right. One recent project that we finished, the GoFlex one, was the largest trial we had so far. So here we have 3 demo sites in Germany, Switzerland, and Cyprus. We have more than 500 prosumers in total, and we use this for industrial loads. You can say municipal loads like water management and so on. We use it for electric vehicles, consumer loads, and so on. Something interesting we have in GoFlex is that we have an AI-based so-called distribution observability service. So basically the idea is here that based on past data and using deep learning, you try to forecast when and where in the grid will you have a congestion, so that the DSO knows this before it happens and can then purchase flexibility to settle, to balance out that congestion. Also, we do automatic multi-objective flexibility trading to serve several purposes, including grid congestion, but also balancing and so on. And basically, the German partner, Stadtwerke Wunsiedel, they found that the value of this tradable flexibility on average was more than 6 euro cents per kilowatt hour, which is more than the electricity itself cost. And they would estimate that if they rolled this out full time, they would have 5 million euros extra gross profit per year for a rather small multi-utility. And the hardware necessary to do the automation and so on, they found return on investment within 2 to 5 years. In the spin out, we have made FlexShape. We have a number of projects. We have a solar predictor that can predict PV supply at any GPS coordinate for the next 5 days. We have a battery MPC controller that can optimize physical batteries or heat pumps. We have a mobile app that can predict and optimize residential loads through recommendations and automatic activations using 20 euro smart plugs. We have a blockchain-based flexibility market where you can basically trade flexibility at a given metering point, at a given delivery accuracy, and a given validation type within a small market like an energy community. And finally, we have an aggregate as a service, which is like a Lego platform for smart energy systems, where you can take different systems and devices and plug them together and then have them optimized. So I hope that you find this interesting and would like to use FlexOffers. And here we have some open source tools. So we have with report and code. So basically this is, there is FlexOffers agents that can control various types of loads. There's also a cloud-based version that can control devices over the internet. And then we have a so-called flexibility manager, which is the one doing the aggregation and optimization. So the FlexOffers agent is the one connecting the devices to the FlexOffers manager. So here we have a backend written in Java, 43,000 lines of Java, where the source code is 28,000, and the front end is about 6,000 lines of Angular. We support washers, dryers, and dishwashers, heat pumps, boilers, and freezers, and EVs and e-bikes with batteries. And we communicate over REST and MQTT, and can also do simulated loads. So the architecture looks like this. And the FlexOffers manager has a backend and a front end again with some 10,000s of lines of codes. And it basically, we get it through this proxy, we get in the flex offers, and then we can handle prosumer contracts. We can do optimization. We can do trading. In ProFlex, we do it towards a local flexibility market called FMAR. And also we have a backend DBMS and a front end for looking, okay, so how is the optimization going, setting configuration parameters and optimizing and so on. We can minimize total costs. We can balance supply and demand. We can, if we have high, we can generate sort of flat high loads, flat low, long loads. We can say, okay, reduce now, low loads now, high loads now. So do you want to ramp up or ramp down right now, and do manual scheduling? The open source code and the documentation is found at this GitHub link. So this is now the summary. I hope I'm on time. So we have flex offers. So basically we think that the new energy system is bottom up, and we should also control and balance it bottom up, and flexibility is the key. And what we propose is a common language for flexibility called flex offers, where we capture flexibility in time, amount, and price. We can handle state, energy storage, energy conversion. It is scalable. We can handle millions of devices and long time horizons. We extract and optimize flexibility with machine learning and AI. We have won several awards for this at World Smart Grid Forum and ACME Energy, and validated it in more than 15 projects with more than 1,000 prosumers in all, and made a spin out. We are happy to further develop this technology in research and demonstration and seek collaborators for that. And then at the end here are some links with info pages. I assume the slides will be shared, videos and so on from the projects about the technology, about the system. We have here the CEO of Stadtwerke Wunsiedel that explains about the GoFlex system and what it does for them, and some links to our new project with, for example, Wunsiedel, the FIBER project. Also a link to the Flexible Energy Denmark project, where we developed the technology in collaboration with, among others, Bo and Grace, who organized the conference, and some references for literature. That's it. So I'm happy to take questions.